Hello everyone, I'm Felicia Brisk, a visualization scientist at the University of Hamburg, and I will present our work, Real-Time Immersive VR Visualization of Ocean Climate Data. Scientific visualizations using virtual reality have been proven to be a powerful tool in the exploration of climate data. We present an immersive VR environment created to help Earth scientists and other users to visualize and study ocean climate simulation data and processes. The goal of our environment is to provide an interactive exploration, learning, and scientific communication tool, enabling users to move around freely and arbitrarily play the simulation in order to observe the evolution of ocean eddies in real time. We focused in this work on the evolution of Northeast Atlantic eddies enclosed by warm and salty Mediterranean water. These clockwise rotating eddies of Mediterranean water origin are called MEDIs for short. The study of the dynamical processes involving the Mediterranean water is important, since this water mass plays a key role in the ocean's thermohaline circulation and thus in regulating the world's climate. The salty and relatively warm Mediterranean water flows through the Strait of Gibraltar and afterwards along the Iberian Peninsula into the Northeast Atlantic over a complex system of underwater canyons and promontories. In the course of this, strong eddies separate from the main flow and spread into the ocean interior. The simulation visualized in our environment presents 1 year of the evolution of MEDIs. MEDIs are shown wandering through the ocean while rotating clockwise and enclosing the salty and warm water, maintaining those properties over long periods of time. During their movement, MEDIs are influenced by other, counterclockwise rotating oceanic eddies. Due to these interactions, MEDIs modify their translation direction and can eventually lose their stability and be destroyed. We used the high-resolution MIT GCM ocean simulation dataset and combined it with the GAPCO bathymetry digital elevation model. We extracted from both datasets a region of interest with the respective selections illustrated in this image. We pre-processed both datasets in a 3D procedural modeling software. The visual representation of the MEDI structures was carried out with the help of isosurfaces. In order to facilitate real-time frame rates in the final version of the environment, we reduced the polygon count with the help of a feature-preserving algorithm, and we removed small noisy features. The bathymetry and topography were modeled as a height field. Height layers were used to establish dry land and ocean floor components in order to allow subsequent height-dependent texturing. Both datasets were then translated in the Unreal Engine 4 game engine. We sought to create an engaging, visually compelling environment. The previously defined height layers were textured with physically based materials. We created a dynamic ocean surface with Gersner waves, and we set up the scene lighting with the help of a directional light and the sky dome textured with a high dynamic range image. The underwater environment was created with the help of a water physics volume with a buoyancy and water friction component that enabled the implementation of a swim-like user motion as seen in this video captured during the early stages of development. We applied the Fresnel transparency shader to the salinity isosurface in order to highlight the lenticular shape and filaments of the MEDIs and allow the visibility of the interacting vorticity isosurfaces. We activated UE4's world composition and world origin rebasing features, which are important tools for achieving real-time performance. Our environment achieved on mid-range hardware 56-58 frames per second, ensuring a smooth visualization with no latencies or artifacts. In order to ensure good visibility of the simulation, we established an active perimeter corresponding to the bounding box of the simulation data. The user is enabled to play the simulation only when situated within the limits of the active perimeter. We included a HUD that displays a circular time progress widget, a color legend, and a real-time sliding map that displays the user location in order to enhance the user's geographic orientation awareness. We use an Oculus Rift Touch HMD and kept the motion controls lightweight and mirrored. The script shows the user entering the water physics volume, where they will be able to navigate with a swimming-like motion. While the user is located within the active perimeter, the simulation can be played or stopped while the color legend and data description are added to the heads-up display. And here is an example of a user observing the evolution and wandering path of eddies of interest. The following captions describe the visual cues we implemented in order to enhance the user orientation regarding their location within or outside the active perimeter. Due to the current COVID-19 related restrictions, we were able to recruit only 5 test participants. Of these, 4 were male, 1 female. 1 participant had a background in oceanography, the rest in other climate sciences fields. After a short instruction, all users were able to adapt to the motion controls and easily interact with the scene and simulation within 1 minute. The participants found it useful to have the ability to dive inside the eddies and observe the inner structure evolution, as well as follow closely with easy navigation gestures the eddies on their wandering paths. Overall, participants had a positive view of our environment, and none of the participants reported significant motion sickness or asked to stop during the experiment. Thank you for listening.